Welcome to Chapter 2, Data Science. This video provides an overview of the data science field. In this chapter, we expand the concept of data into data science, focusing on how data is collected, processed, analyzed, stored, and used for decision-making. We will also introduce big data concepts and the Hadoop ecosystem. After completing this chapter, you will be able to explain data science, identify the roles of data scientists, differentiate between data and information, and describe the data processing cycle. You will also be able to explain data types, describe the data value chain, understand big data characteristics, and explain clustered computing and the Hadoop ecosystem. Data science is a multidisciplinary field combining computer science, statistics, mathematics, and domain knowledge. It uses algorithms and systems to extract insights from structured, semi-structured, and unstructured data. Data science is important because it helps organizations make data-driven decisions and converts raw data into meaningful insights. It enables prediction, optimization, and automation, supporting innovation across various sectors. The role of a data scientist involves collecting and cleaning data, analyzing large data sets, and building predictive models. They communicate results to non-technical users and support strategic decision-making. Data consists of raw facts and figures that are unprocessed and unorganized, such as numbers or text. Information is processed and organized data that is meaningful, useful, and supports decisions and actions. The key difference is that data is the input, while information is the output. Data has no meaning by itself. Information adds context and value. For example, raw data like, quote, 80, 90, 85 feet becomes information when context is added, such as average exam score is 85%. The data processing cycle has three main stages: input, which is data collection and preparation; processing, which involves calculations, sorting, and transformation; and output, which is the final information used for decision-making. Data can be classified from two perspectives: programming and data analytics. From a programming perspective, data types include integer for whole numbers, Boolean for true or false, character, float for decimals, and string. In programming, data types are important because they define allowed operations, control memory usage, prevent errors, and improve performance and reliability of software. From a data analytics perspective, data is categorized based on its structure and ease of analysis. This includes structured, semi-structured, unstructured data, and metadata. Understanding these is essential for big data applications. Structured data fits into fixed fields and tables, organized in rows and columns, making it easy to query and analyze using traditional databases. Examples include relational databases and Excel spreadsheets. Semi-structured data does not follow a strict tabular structure, but includes tags or markers for organization. It has a partial and flexible format, with examples being JSON files and XML documents. Unstructured data lacks a predefined format, making it difficult to analyze without advanced techniques like machine learning. This data type forms the largest portion of big data, including text, images, audio, and video. Continuing our discussion on data types, metadata is data about data. It provides descriptive information that improves discoverability, management, and analysis. An example is the date, location, and camera type embedded in a photo file. The data value chain represents the flow of data and shows how value is created from raw data. This process is essential for big data systems to convert collected data into useful insights. The data value chain stages transform raw data into valuable insights. These stages are sequential but often iterative, and effective data science relies on managing them properly. The first stage is data acquisition, which involves collecting, cleaning, and filtering data, requiring strong infrastructure to ensure data quality at the start. Next is data analysis, which focuses on extracting meaningful insights. This involves cleaning, transforming, and modeling data to identify patterns, trends, and relationships, supporting informed decision-making. Common techniques include statistics, data mining, and machine learning. Data curation is the third stage, managing data throughout its lifecycle to ensure accuracy and reliability, making it reusable and accessible. Following this is data storage, which involves storing data in scalable systems, often using NoSQL databases for big data. The final stage is data usage, applying data insights in real-world scenarios to support decisions and improve efficiency. Big data involves extremely large and complex datasets that cannot be handled by traditional systems, requiring new tools and technologies. What defines big data is its sheer volume, high speed of generation, and variety of sources. The characteristics of big data are often summarized by the 3 V's: volume, the huge amount of data; velocity, the speed of data generation; and variety, the different data formats. 2 additional V's are veracity, data accuracy, and value, the benefit derived from the data. Big data analytics is expected to reach over $655 billion in market value. Examples of companies using big data include Uber for demand prediction, Here Technologies for self-driving cars, and Sophia Genetics for healthcare data. Clustered computing refers to a network of linked computer systems, or nodes, programmed to perform the same task. It is a type of distributed computing that links computers on a network to perform computational tasks, increasing power and functioning as a single computer. Clustered computing handles large-scale data processing efficiently and improves performance and reliability through fault tolerance. It is easily scalable and reduces dependency on high-end single computers, making it essential for big data and real-time analytics. Hadoop is an open-source big data framework and an example of clustered computing. It enables distributed storage and processing, designed for scalability and fault tolerance. Key characteristics include efficient handling of big data, use of low-cost hardware, and automatic handling of failures. The Hadoop ecosystem consists of several components. These include HDFS for distributed storage, Yarn for resource management, MapReduce for batch processing, Spark for in-memory processing, Hive and Pig for data querying, and HBase as a NoSQL database. The Big Data Lifecycle with Hadoop describes how big data is handled from start to end, integrating Hadoop ecosystem tools at each stage. Tools like Scoop and Flume are used for ingestion, HDFS and HBase for storage, MapReduce and Spark for processing, and Hive, Pig, and Hue for analysis and visualization.